Another online meeting for MTH129 Discrete Maths. So this week I'm looking at asymptotic notation, or pretty much Big O. So Big O is a way of describing how functions grow, essentially. And they're called asymptotic notation in the sense of how they behave as the size gets really big. And so normally we think of this in terms of algorithms. You've got an algorithm, how you work out how does the algorithm perform when you've got a rather large input, either in terms of time or how much memory it uses. And so Big O is used to describe lots of those sort of things. It also is used in other things. That's cropped up from number theory originally. And so it's just a way of finding sort of the long-term sort of behavior. So it's really about sort of growth classes. So although you can sort of prove it all formally, it's normally good to have a bunch of good to think of a bunch of classes. So try to do it a bit more intuitively. So just writing things down. So the bottom class we would normally encounter in practice would be constant time. So these are functions which are just constant, or constant after a while, if nothing else. So they're stabilized to their constant time. That's sort of the bottom class that we'd encounter. Other sort of classes, I won't put them all, but another class is logarithmic functions. So these are functions which grow in logarithmic time. Next is something like linear. Next one you encounter. So I'll just explain. It's good to have some pictures. So I've done this in class. So basically, you've got a function on n, and n would be, for example, input size. So if you got a function, if it's on list, it'd be the number of elements in the list, etc. And the vertical axis here depends what you want to do. So if you want to do some time complexity, that would be the number of, say, operations. You could also do time, physically how much time it takes, which is very much information dependent. But so can a number of operations directly, or if it's got a memory, it's the amount of memory space it would be. So that's sort of the function. So you might have some sort of function which sort of grows like that. Most functions, the bigger the input size, the more number of operations are required. It's normal, so they tend to be increasing, but they don't not be uniform, etc. So what big O means is if I can draw this whole function between two different straight lines, these are two different straight lines there, then this would have big O of n. So essentially, if I can fit I can fit my various function here between two constant multiples of the line, then it's in big O of n, or actually more precisely, it's in big theta of n. So big O is the idea of something weighing less than or equal to. It means it's bounded above by this red line. So if I know it's less than this top line here, it's in big O of n. If it's bounded between two straight lines like that, it's in big theta. The much more common notation used both in this subject and elsewhere is big O. Big theta is probably more useful, but it isn't used very commonly. There's reasons why I could speculate, but that's sort of how it goes. So big O just really means it's bounded above by a certain function. So in a sense, basically what it really boils down to is what happens after a while. And again, as I've drawn it like here, these lines, if the function actually can go above the line, as long as it stays below the line after a while, then that's what big O is. So it doesn't actually care what happens earlier on. It happens looking at the bigger picture, which is good for sometimes, as you can see, that's a weakness of big O. So what it really is, this upper line is really just to give you an idea of how it grows toward the end. And so these are different classes. So constant, logarithmic, linear. Next sort of common one is log, linear, quadratic, and we can go on. And so basically gives you some other ideas. So I just put some more in here. If you do log to any power at all, so if you had log to any power, so 1, 2, 3, 4, 5, 6, etc., all of those certainly grow grow slower than a straight line does. So all these are sub-linear in that sense. And so what log time is, so log is sort of a bit like n to the power of 0. So it's almost like constant time in that sort of sense. That's not quite true, but in terms of how calculus sort of works, if you ever know calculus, the derivative of log n is n to the minus 1. And so in some sense, it's sort of like n0 in terms of the ordering. So that's really rough. But essentially, when the order here, if you see a log n, it's almost like saying that's n to the power of 0. So it's almost like n. And if you've got lots of them, it doesn't actually bump it up into the next class and on. It always just separate. So how it basically works is you've got these are all called polynomial time. Log, as I said, is a bit like n0, so that's always fits under linear. If you've got n log n or n lots of logs, it's always between the two different phase of n. So all the polynomials, and all those sort of functions are ones. So anything which is done in polynomial time is considered doable. Then you've got the classes after that which are not so doable, and they're ones that are more than polynomial time. And so the order for that is exponential, so some number to the power of n. Then you've got factorials. And then lastly, you've got n to the power of n. And knowing that order is important to be able to answer questions. And so as I said, you either remember it, or if you don't remember it, just have it written down. And lots of things at the beginning are easy to remember. Remembering where the logs are is tricky, because people aren't necessarily familiar with logs. And remember the top ones, but remembering the order of polynomials is fairly straightforward. So let's just do some questions. So what I want to do is for each of these, just work out what the big O for each of them is. And big O really is is a bit rough. So you can do big O's for lots of them, but it's useful just to have the basic class. So I've got a bunch of classes of growth classes at the top, effectively. So let's work what they are. So let's put it in one of these ones, essentially. So the way to do it for any of them, so the first 4 examples here, I've got a sum of different terms. So I want to know how it grows in the long term. So it's always about happening in the long term. So as n gets really big, so as the input is sort of the idea, each of these terms will change. What often happens is some terms will grow much quicker than the others, and after a while, the other will just become insignificant in comparison. So if you look here, I've got n log n and n essentially as my 2 basic terms. The constant in the front, 10 and 100, don't really change how it grows as such. They're just sort of constant multiples, so they don't change how it grows. So it's really the n part which change the growth. So if you look at my little list here, I can see that n log n and n are the 2 classes, and I can see that n log n grows quicker than n does. So as n gets bigger, this first term here will dominate. So put in other ways, if you make it n big enough, the front here gets bigger than the second term. So for example, if you chucked in n equals 1,000,000, log base 2 of 1,000,000 is about 20, thereabouts. N would be 1,000,000, so you've got about 200 So you've got 200 million is the first term. Well, the second term would be about 100 million. So you can see when your time n equals a million, this first term here is actually bigger. If you sub in really small numbers, it's the other way around because of 100, but after a while, the first term gets bigger. And that will dominate. And so essentially the big O class really is determined by the term which has the higher, grows the quickest. So putting it away, to answer A, B, C, D, just look at all the options, look at each term, pick the term which grows the quickest using our list, and that would determine the big O. So this function would have big O of n log n. And there's different ways of saying it. You can just say is the standard way. I normally think of it being sets, so I would say the set containment, for example. So yeah, the little e symbol is fine. You notice when I dropped it, I dropped the constants. So I dropped the 10 and the 2, and the reason is because big O doesn't care about constants. It just talks about up to a constant multiple. So that's the first idea. That's basically the idea. So let's look at 1b here. What's the big O class for 1b? And what I'm really asking is there's 3 terms there. As n gets bigger, which one grows the most? That's right. So you've got exponential, factorial, and n to the n. They're the top 3 classes here, and the biggest of those is n to the n. That's the answer. Next one, this is so in truth, I could think of algorithms which sort of are like 1a in terms of their time complexity. 1b is completely made up. 1c is possible. So what's the big O class for this one here? The 1c. So again, you've got 3 different terms. Which one, as if you make n bigger, which one grows more? Came in twice. Yeah. So you got 3 terms. The 1,000's big for the moment for small ones, but if you make n big enough, it gets swamped to the 1,000. And so the highest for a polynomial like this one, it's really just the highest order, highest degree, which determines it, just like you said. 1D. Yep. So, and again, the trick for this here, in case people watching the recording don't really know, root n is n to the power of a half. And n is n to the power of 1. So really I'm comparing n to the power of 1 and n to the half. The biggest power, n to the 1, would be the dominant term after a while. And so really it's this first term, the linear term dominates, so on is the linear one. And although I've specified them all like this, I mean, you can they are big thetas, for example. So they're big. So as I said, big O is really the idea of being less than or equal to a certain growth class. Big theta means equivalent to that growth class. Sort of how I often talk about it. So with 1e here, the way I would do it intuitively is to take the bottom and top separately. So if as n gets bigger and bigger, there's 2 terms on the top. Which one dominates? So which has the highest growth class effectively on top? Is it the 5n squared or the 6n cubed? Yep, so it's pretty much the 6n cubed would dominate, and being more precise, the top is big theta n cubed. The bottom, in the same sort of way, would be dominated by the highest order, so 5n squared. So as n gets bigger, effectively that's what it looks like after a while. You can cancel things out. And so you're going to get 6/5 n. And that tells you that, well, that's as n gets bigger and bigger, it sort of looks like 6/5 n. And that therefore the whole function will have big O of n. Putting another way, the top really is big theta of n cubed, being a little bit more precise. the bottom is big theta of n squared. And so if you take the ratio of those two things, the whole thing's big theta of n cubed on n squared. So it's actually equivalent. So as you make n big enough, it's actually bounded between two different straight lines. So like I've done before, after a while, it'd be flowing between two different lines. And you can work them out if you wanted to. But so with these big O stuff, there's multiple ways of handling it. And so I think the intuitive understanding is going to be much more useful in the long term when you encounter these again later. That's what I encourage you to do. And this is what I'm trying to show. And the way of doing it, you don't have to be super formal with the notation like I'm not being formal actually, but the big thetas I was referring to. So the last one's a little different. I haven't mentioned this in lectures. Here I've got a sum, so 1 plus 2 cubed plus 3 cubed plus 4 cubed, etc., until I can keep going to n cubed. What's the big O class here? Now, it might be tempting to do how we did it for the previous ones, to go, well, the n cube's the biggest term, and so therefore it's tempting to say it's big O of n cubed, which is incorrect. And the reason why that's incorrect is because we don't have the previous cases there was just a fixed number of terms. Here the number of terms is growing. The number of terms is n. So as the input size increases, we're getting more and more terms. So we have to worry about the number of terms. So how to tell you the slow way, and then I'll explain the quicker way. And the quicker way is what I would encourage you to do. So big O, which is all we ask for, really is just looking at upper bounds. So that's less than or equal to idea. So let's just make this less than or equal to various stuff. And the top term is certainly less than or equal to n cubed, but all the other terms would be also less than or equal to n cubed as well. And the reason is just because n cubed's the last term in the series, that was the biggest term. So if I add up lots of n cubes, there's n of them, so I'd end up getting n times by n cubed equals n to the 4. So essentially, as n gets bigger, whatever this function is, it's certainly less than n to the 4. And therefore, that provides an upper bound. So therefore, this series certainly is bounded above, in terms of its growth class, by n to the 4. And so it's in big O, n to the 4. Now, at first glance, you go, maybe I could do better. Maybe I could shrink down this to something a bit smaller and still be accurate. But as a matter of fact, that's actually accurate. So it's actually big theta of n to the 4 even. That's the slow way. But you can imagine if you had any series at all, you could do the same sort of trick. You just make them all less than or equal to the highest term, and therefore, so if you've got any series, so you've got a bunch of, so you've got f1 plus f2, etc., all the way up to f to the n, then essentially you use the same trick. You're going to end up getting, this is in big O of n, lots of the top term, fn. And in terms of code, normally a sum like that's just another loop. So essentially, for every extra loop you do, so you multiply the big O by n is approximately what you're going to do. Now, if you're looping over counting numbers, that is, it'd be n. If you're counting by doubling the number every single time, which is sort of common in sort of recursive divide and conquer techniques, then if you're doubling every single time, when you're looping it over, you'll get a log n rather than an n factor cropping up. And so where we see log n's and n's, that's the reason why you get lots of them. So n is a loop over a whole array. Log n is skipping, is a doubling how much you're going each time. So it's a divide and conquer concept. So that's the idea of how you work out big O for various functions. And although some of these are completely theoretical, those techniques that I need to do these ones here helps with actual practical ones you might encounter. Okay. So let's just copy this. We had at the top. So that's the order we have in our back of our mind here. So basically, I've got a bunch of functions, different growths for them. I would like to order them in terms of big O, so order them in terms of their long-term growth. So if you sub in n equals 1, for example, so a really small input size, then that one's the smallest because it's 0. Then this one is really very small as well. And so when you got really small inputs, you get a different size. But when it's something small, the computer can do any small stuff really quickly. That's a bit irrelevant. It's what happens when you've got rather large data sets is when it's going to really make a difference to a computer. And that's what we're concerned about. What happens when the input size gets really big? So out of these, which would come first? So again, looking at the list, I'm looking for constants first. So are there any of these functions that are constant? And it says no. So then next class is some sort of logarithmic ones. And so although root n's tempting, actually the log here, even though it's cubed, is actually on the bottom here. And as I said, the way to sort of remember that, I think, is think of a log and really is sort of like just a slightly bit bigger growth than n to the power of 0. And so even though you've got it cubed here, it's still n 0. So 0 times 3 is still pretty much 0. So that really is at the bottom here. The next one is n to the half, or square root n, as you correctly said. So that is the second one. But the logarithms really fall under every single thing else, which seems a bit surprising. And so let's just to give a sense for it. So you subbed in a million. Let's give it I suspect it takes a while for it to give me here. But if you sub in a million, then log base 2 of a million is 20. 20 cubed is 8,000. So I've got 8,000 for the first one, which is bigger. Square root of a million is 1,000. So even at that point in time, this first one's bigger. But if you keep going more and more terms, so I've got to start putting a really big number in here for this to start, for the root n to start overtaking it. But it's true. So if I subbed in, I think I've got something I can take square roots of easily. So I've subbed in, was it 1 trillion? So log base 2 of 1 trillion is 40. 40 cubed is 64,000 thereabouts. The square root of a trillion is equal to a million. So you can see that after a while, root n does overtake. It takes some time though, and therefore, if you're only considering moderate size stuff, then maybe the root n algorithm actually is preferable. But if you've got really, really big inputs, the order makes a difference. But anyway, on the side. So that's the first two. What comes next? What comes next? Yep. So the next one is going, well, the basic idea is I'll do all the ones that polynomial time. So they're the ones with either logs or power or polynomials or combinations of them. And you just do them in order of power. So the next one you just say is the linear one. And the 100 and 100 don't make a difference. The next polynomial one is this n cubed. So the fact that it's been divided by 10,000 there makes it really small, but it does mean after a while it does grow to swamp all the other ones. So that's all the polynomials. The next lot you've got to have the exponentials and then the factorials and into the end. So looking in here, I've got a factorial. So I've got two more. And so the factorial is going to be the end here. That's that sort of class. But I've got to do the exponentials next. That's what's in between. And I've got two to choose from. Now, the first one is a straight exponential. The other one's not. It's got an n squared times 1.1 to the n. Which of these two do you reckon is the smallest growth, smaller growth class? So if you subbed in really big values of n, which one would give you smaller values after a while? And the answer is the other way around, unfortunately. So the answer, and the whole purpose of doing this is to learn from it, right? So make a guess and get it wrong, who cares? We're all learning. So the answer is actually 1.1 to the n squared in the long run is smaller than 1.2. Let's just try to think why that might be the case. If you make n really, really big, then basically you've got 1.2 times 1.2 lots and lots of times. And each of those factors is greater than 1.1. If you start getting lots of them, that repetition of 1.2 really does start swamping. So the moral of the story is that these exponentials really do swamp out everything else. So this exponential here really does beat any other polynomial, and that's what really dominates these. Now, being more formal, so if I do 1.1 to the n times n squared, if you divide it by 1.2, so basically I want to say that's sort of bounded. So that's equal to that's equal to n squared all over 1.2 or 1.1 squared. That's sort of close to n squared and 1.1 to the n. So roughly speaking, I'm just on the division. So if you take the ratio of the two, that's what we get. And as I've said, these exponential here really does swamp out after a while the quadratic. So as n gets bigger and bigger, the top getting so much bigger, and so that's pretty much 0. So that suggests that as n gets bigger, the top's getting bigger and bigger and bigger, and really does swamp out the bottom. So that suggests that one's bigger after all. And so the moral of the story is exponentials swamp out anything else. So if you've got a few extra terms in front of an exponential, it's really just the exponential term which is really going to determine the growth rather than anything else. As n gets bigger, the n squared isn't really going to make much of a difference, which seems surprising, I'm sure. And so the real lesson is if you've got any algorithm or memory usage which is exponential, it means it really is going to take up a lot of space and probably is best to be avoided if you can. And so in class, the exponential algorithm I considered was the Towers-Fenoy, and that suggests that the Towers-Fenoy, if you want to start making a game for people, don't make the input size, which is the number of disks in Towers-Fenoy, too big. Otherwise, it really does get completely unruly and unuseful. So if you had 10 disks for the Towers-Fenoy problem, you're getting over 1,000 different moves just for the optimal case. Chuck one more disc in, it doubles it to over 2,000, and that doesn't really make a useful game. So having some idea of complexity really shows the limit you can push for the game. And so towers are always a simple one, but you might design other games which are based on, say, a 5x5 grid, and you're going, okay, that's certain input size. What would happen if I make it 6x6? And if the whole thing is exponential, 5x5 might work fine, but it might just getting so much more complicated just adding that slightly bigger grid. And so that game 1024, if you've ever played that game, again, how well does that scale to bigger ones is sort of the question. And having some sense of how it grows does inform those sort of things. Sometimes play testing. Sometimes you're working out by play testing, of course, just mucking around. But having this sort of sense of growth is important for lots of sort of development. Okay. Just want to finish off with just an example of how you might use this in practice. Okay, so I want to mention two different algorithms for evaluating a polynomial. So a polynomial, so this is an example one. This is just quadratic, but it can be anyone. So in general, the way you'd store a polynomial in a computer, say, would be just have an array of all the different coefficients. You have an array called coefs for coefficients. And if the highest power is n, you'd have an array starting at 0, ending at n, which would have all the different numbers. In practice, these coefficients probably would be doubles, so floating points or decimals. And so what you want to do is you want to evaluate the polynomial. So you go, I've got a number x, so I know what I've got x equals 1.5. I would like to sub it into my polynomial to get my answer. So that's basically what I want to do. So I want to how different ways to evaluate it. So I want to look at two different algorithms for doing it. So option one is to do it like you think like I would do it by as a person, and that is just break it down. So by person, I actually might start with the 5. So I'd get the 5 first. Then I'd add it to 2 times by x. And then I'd get a result. And then I'd add 3 times by x times by x. And got that result. So that's sort of how I'd do it by hand. I'd to work out 3x squared, I'd square 1.5, you have 2.25, multiply by 3 gives you whatever answer it might be. So that's sort of how I do it by hand. And that really is working out term by term and adding them all up. Let's work out how efficient that is. Okay, so let's got some code just to be able to talk about it. Okay. So this is some computer code that sort of describes that is a way of the algorithm. So essentially the algorithm is step 1, start with the constant coefficient, which is this one here. That's a starting point. Start with that, the constant term. Then you want to loop over all the other terms in the polynomial. So what do we have? We had 3x squared plus 2x plus 5. So it basically says, let's start with the constant term. Then for all the other terms, so just loop over all the other terms, work out the term by working out the coefficient, so 2, multiplying by the corresponding power, and add them up. So work out 2 times x, and then work that sum out, work at the next term, add them up. You just keep going. How you work out the powers, so I've written it down just to understand how the powers really work, is how you work out the powers. If you decided to ask for a power of 0, you just return the number, you wouldn't actually do any multiplication. Otherwise, basically how you work it out is you'd keep multiplying x by itself until you get the answer you need. That's pretty much how you're going to work out any powers. Let's see how many operations it is. Now, if you think about it, x and the result and these coefficients here will all be doubles or floating points. So these are all decimals, and whereas so it's the loop counter and the size of the array would all be integers. Now, you have to do operations in both in the integers, so you actually add them up, add 1 to them, etc., and check if they're equal. So there is some integer arithmetic involved, which does take some time, but the floating point arithmetic tends to be much slower than that. So if you've got starting with 0, adding 1, pretty quick operation in a computer, but floating point requires a lot more operations. Certainly things like multiplication of floating points is going to take a bit more time. And so we're trying to work out how efficient it is. In terms of how quick it's going to go, really is these number of floating point operations going to be the real dictator. And so what I want to do is I want to look at the number of floating point operations, and for short they're called flops. So I want to look at the number of flops. So first of all, let's consider this power x to the I. So this is essentially working x to the I. How it's working, like you can read the bottom here, really is just doing x times by x times by x. So if you had x by itself, that'd be no flops. Like there's not really doing anything. If you had x to the x squared, you'd have to do x times by x. So that'd be 1 flop. So 1 multiplication effectively. X cubed would be x times x, give x squared, times another x. So there's 2 multiplications. So in general, to work at x to the power of I, it has to be I minus 1 multiplications, or flops. Let's put multiplication in here. We have a multiplication symbol, so there's another 1 multiplication. And I've got a plus, so I've got 1 add. So on this line over here then, in total, I've got 1 plus 1 plus I minus 1. To add them up, I've got I plus 1 flops, floating point operations on that line. So that's pretty much what it's doing. So to work out each term, which is what it's really doing here, is it's going to take I plus 1 operations just to get the next term and add it to my current result. So let's look at total number of flops. So to begin with, I chuck my constant in there. That's not really doing much. Then I start the loop with I equals 1. So for I equals 1, I'll have 1 plus 1, or 2 floating operations for my first go of the loop, which is really just working at the linear term. Plus, next time I do the loop, I will be equal to 2, and so there'll be 2 plus 1, or 3 floating operations for that iteration. Next time will be 4, etc. And the last time the loop goes through is I equals n, and therefore there'll be n plus 1 floating point operations. So the total number of floating point operations for this sort of approach would be given by that sort of series. Do you know what that's equal to, by any chance? You may not. It's fine either way. Just curious where you're up to. So, depending what you've done at school, this is true of everybody, then this is, you may or may not know what it is. So, a few things. I'll work out the sum explicitly in a second. But what we really want to know is, what's the big O for this algorithm? So what's the big O for the number of flops? And we want to do this because the big O is just a useful way of comparing the algorithm. So the number of flops here would be, well, I've got, that's a series, so like the trick I did before the series before, the big O for a series would be just the number of terms you've got, so n, times by the big O for the largest term. Now I could write it as n plus 1, or I could just write, well, the big O for the largest term is just n really, and so the big O really is n squared. And you can see that in terms of the code, you've got 1, 2 nested loops. So if you've got a single loop, it tends to be linear. If you've got nested loops here, which you do just buried in functions, you tend to get n squared. So the big O for this particular algorithm is n squared. Back in terms of how you do it explicitly, so that's just the rough way. If I just know explicitly how many flops there were, which is also helpful, I can sum up. So this is called an arithmetic series. So basically, for summing an arithmetic series, it's the first. So an arithmetic series is when the difference between each term is constant. So the difference between each term is 1 every single time. So to work at arithmetic series, you do the first plus the last terms, divide it by 2, and you multiply that by the number of terms. So in this case, I've got beginning, first is 2, the last is n plus 1, divided by 2, and then multiply how many terms there are, so multiply by n. So that's equal to, in factorized form, n times n plus 3 on 2. Now, you don't, so the point is, why I did the first way first, is you don't actually need to know how to get the explicit sum to work out what the big O notation is. And so big O, although it's a bit rougher and doesn't give explicit number of flops, it's still nevertheless useful for comparisons, which I'll show in a second. But that's the actual number of flops. So you can plug in, if I had a polynomial of degree 5, so n's the degree of the polynomial, I could do 5 plus 3 gives you 8 by 5, 40 divided by 2 is 20. So it requires 20 different operations to evaluate, floating point operations to evaluate a polynomial of order 5, for example. And that's sort of how it grows. That's the first sort of algorithm. Okay, so let's do a second one. So second algorithm. How this works is, the slight problem with the last one is it's doing all the powers, it works out the powers every single time. So it doesn't actually remember the fact. So when we, in this case here, if you were to work out x cubed, to work out x cubed, you actually have to work out x squared all over again. So it doesn't actually remember the results it already has used. And so you can make this more efficient a few different ways. One is to remember the values it's already looked up. And so you might produce a lookup table. So that's sort of a useful technique in other situations. But in this case, we don't have to worry about lookup tables. We can do it just by multiplying carefully. So I'll explain the algorithm by just doing this case. So you start with the leading term, 3. Every single time you multiply it by x, and then add on the next coefficient. The next stage, you multiply the whole result by x, and then add on the next coefficient. And so, giving a bit of a longer example, so I've had 7 x cubed plus 3 x squared plus 2x minus plus 5. They could be minuses in floating point 6. I get the 7, multiply the 7 by x, add the next coefficient, 3. Evaluate that result, so it gets a number. Multiply that by x plus the next coefficient. Evaluate the whole thing. multiply the whole result by x at the next number. And you keep going until you hit the constant term. So if you look at it, what I'm really doing here is, between these two here, I've just sort of partially factorized. So I factorized some of the x's out. And by doing so, I'm actually not having to work at lots of intermediate results all the time, or not repeating myself. And so this is in trying to be more efficient. Let's see if it really pans out that way. So an algorithm for it, which might, in terms of the code, which may or may not help you. So how it works is you start with the leading term. So start with the leading term, and then you loop over all the other terms. So you go from the term just preceding that all the way down to the bottom. So all the other coefficients, and you get whatever result is multiplied by x, add on the next coefficient, which is sort of what I explained, and that just end up building up the whole thing for you. So I want to count the number of floating point operations. So in this case, I've got one add and one multiplication on one line. So this line here would have in total 2 floating point operations, 2 flops essentially. So we've got 2 floating point operations. And so the total number of flops would be, well, so for the first time, I'd have 2 flops. The next time I'd have 2. It's 2 every single time. So in this case, it'd be, the total number of flops would be just 2 times by the number of times I have to do the loop. And so since I start or finish it, if you want to look at, so what's I want to do, start at n minus 1 and keep going down till I get to 0. Counting, I got 0, 1, 2, 3, n minus 1. So I'm actually having n terms in the long run. So 2n all up. And what's the big O for this? Yeah. So this one here is, so the first algorithm was big O n squared. The second algorithm is big O n. Which is the better algorithm? So if you had to pick between two, Wolfram Alpha. So you had, Wolfram Alpha is powered by Mathematica. So say you were coding up, so people who design Mathematica, or there's lots of programs, MATLAB, Maple, they're all sort of similar sort of programs. All of them would be able to represent polynomials internally quite nicely. What algorithm would you pick to evaluate a polynomial? And the answer is, well, which one's more efficient, essentially? And the big O in the linear term is better than the quadratic. So you pick this second algorithm in preference. And so similar tricks. If you want to evaluate compound expressions, instead of calculating the same values over and over again, using lookup tables can make things more efficient. In this case, you can do it all in place quite happily. Lookup tables can take memory, and so you normally have a trade-off there. But that sort of, this gives hints to more efficient programming. But you can see that thinking about time complexity and using big O just as a rough rule to try to gauge efficiency for bigger inputs is a useful technique to analyzing code and therefore picking your better algorithms. In practice, you have to do coding. I mean, don't know, it depends where you're heading, where you have to do coding yourself. Sometimes you just, you might do not much coding and use data structures other people have got. But if people have actually made data structures already, they will often give big O for the various operations they can use, and you can use it in an informed fashion. Go, I understand what big O means. I can see that I really want to do appends. I really want to do appends for my data structure, just adding things to the end. Out of the choices I've got, which of these data structures works very efficiently for appending? And that's the one I should pick, etc. And so you can use this as a way of gauging, because data structures are designed for certain, are better for some applications than others, and you have to choose the appropriate one. And Big O is one way of helping you to decide. So that's all I was planning to do today. So what I'll do next week is looking at recurrent relations. And I'll just tend to focus on, so recurrent relations, there's two different processes mentioned in the study guide, and I'll do in lectures 2, the characteristic equation method and the generating function method. For sake of time, I think I'll just do the characteristic equation method in this class, but if you or anyone else listening wants to otherwise, just fire away. But anyway, I will see you next week unless you've got any questions.